Yes.
Okay. Okay. So so before I start, before I start, any question from previous lecture or like the homework, anything? Okay. So if you don't have any question, I'm going to start this week. Let me see if it's recording. So I'm going to start this week pre-session, which is introduced to the comparison between classification models. Okay, so I have uploaded this PDF file on Canvas, and then so this one is available on Canvas already, and then you can choose if you want to make notes on the PDF file, or like you want to write down notes. Okay, so here's the thing. So this is the first part for this pre-session, R setting, initial setup. This one is the same as last week. So we have introduced several packages. So you do need to load the installed package class for the KNN regression, and then require the mass package for the LDA regression. And then, so these are just initial setup as last week. So we want to run all the, so I'll load the data and then create dummy variables. All the things are similar as last week. And then the first thing we are going to introduce is why we are introduced like logistic regression, linear discriminant analysis, or like why we introduce the quadratic discriminant analysis. So the main reason for this one is just linear regression is not appropriate in the case of qualitative response. And then suppose like you're thinking about like a binary case in which we only have the the results, the independent variable we want to not analyze. It just contains values 0 or 1. And then in that case, if we run linear regression like OLS or some other things, the results may fall out of the interval, like fall out of 0 and 1. So as like if we just use OLS regression, and then that is possible to get larger numbers like 2 or 3, or even smaller negative numbers. So actually we want the values to fall into the 0 to 1 interval, and then that's the main reason for us to use logistic regression. And on the other hand, we want to use logistic regression because it tests the probability of certain things that may happen in that case. And then, so for the details, please refer to the chapter 4 in the introduction to statistical learning with application AR. Okay. And so first thing is we do the same thing as last week. So we divided the data into 2 subsets of data, which is train data and test data. And then we want to, so the train target, this will be the target from the training sets. And then, so let's first check the train data. Here. So the train sets, as you can see, we have 524 observation of 19 variables, and the test data contains 136 observations. So this one is just how we divided the whole data sets into 2 subsets. And then we want to have the train apple one, this one. So this one meaning it only contains like the regular price and eco-label apple price. And then we want to separate those from the subsets. And then, so the K nearest neighborhood regression, this one used as we have introduced like 2 weeks before. This one, you can check how it works. So this one actually takes several arguments. So the train data sets, test data sets, and also the factor of use classification of training set. And then we want to select the number of neighbors considered. So in general, we will use the cross-validation, which introduced last week, to determine the k here, but for simplest reason, we just use k equal to 3 here. So it will, this regression class, this classification for test sets from training sets, this one just use like the k nearest training sets vector that are found, and they use that one to classify if the testing data is belong to which kind of classifications. And so this one is just we use, and then you can see like there's all other things, like if you want to introduce prop or other arguments here. And then always you can try to check the KNN.CV. This one is k nearest neighbor cross-validation classification. So this one contains classification. Okay. So like so after we first run the regression here, and then we want to check the first 10 predictions, and then so we compare the testing sets, the prediction, and the true data. As we have seen last week, this one created a table for the testing sets. So when the prediction equal to 0, there are 10 true value are zeros as well. So there's like together like 87 observations are correctly predicted, and then there are like 49 like observations are incorrectly predicted. And then use the mean kn.predict equal to test the true value, we got like 63.97% correct predictions based on testing data sets. And then this one is roughly it's not like that good, so we want to improve our results. And then the reason for us to improve introduce different kind of classifications is just because there's no one like exactly one classification can be used for all the data sets. And then as we have introduced k nearest neighbor classifier, this one is non-parametric classifier. And then for logistic OS and other classifier, we do need to assume distribution before we do the regression. And then that one is we generally refer those as parametric classifier. So one thing to improve the prediction results, we want to add more features. But in general, in KN classifier, as we have introduced, as we have more factors in the model, in general, the results may be better or may not. And most likely, they may not give you a better results. So this one is introduced in the, I think introduced in the chapter 2 or 3. So we just covered last week. And then that one is just because the KN classifier may be a straight line rather than a true classifier in this case. And then let's see what will be the results after we introduce more features here. So similar result, similar step as before. So we have the number, the table, which is so this one we because so one thing problem here is just I use the same notation, same term for the KN prediction based on different kind of features. I use the same notations. So every time when you try to rerun if you use the same notations, every time when you try to get the results, make sure you do use the correct training data and then the test data sets. Otherwise, the results may be confused. So here, after we had more features, the results is actually the percentage declines from 63% to 58%. So actually, the prediction does not is worse than the previous one, and then is because when we introduce more features, the non-parametric classifier may not perform as good as before, just because more features may introduce some noise, and then it may mislead the results. Okay. These are just same thing we have introduced before. Any questions so far? Okay. So next thing is we are going to introduce the logistic regression. So we have done the logistic regression last week, and then in general, the key point for the logistic regression is this function, which is we use this logistic function to calculate the prediction probability of x, and then we use a method called maximum likelihood to fit the model. So you can see how we do derive the maximum likelihood in the textbook, or like the professor has introduced. He has uploaded a file on Canvas. This one. So this is the multi-logit regression, and then so you can see how he calculated the maximum likelihood results, and then so in general it just take the. So assume we have n observations, and then we take the likelihood as this one. So this capital pi just represents for like all the like P1 times P2 times until PL. So all just the multiplication of PI for I from 1 to L. Okay? And then you just take the log form of this function and then get these results. And then just in order to maximize this one, you just take the derivatives and then get the results. So you can go over the derivations by yourself. And then this one will be the results for in this case. So in general, we use maximum likelihood to fit the model. And then in R, you do not need to manually enter all the details in R. So just one line of coding will give you the results. So here we attach the data, and then we do the logistic regression. When you summarize the regression, you can see the results as we have seen last week. And then we predict the logistic. So we use coefficient from logistic regression to predict the if the family will buy eco-label apples based on test sets, and then we get a summary, something like this one. And then we need to classify the results. Like you can see, we have this one is actually a bunch of number between 0 and 1. So we need to classify when this value is bigger than 0.5, then it's classified they will buy if the probability is bigger than 0.5. And then for the probability less than 0.5, the household will not buy the eco-labeled apples in this case. Similar as before. So we got this table, which is here. This is the result. So based on logistic regression, we actually get like 69% correct predictions based on so when we train based on the coefficients from the training data. And then, so compare this one with previous one, like for the KN results, when we have the same number of features, education, age, family income, household size, regular price, eco-label, apple price. So all these price, same features. The KN classifier gave you 58% correct predictions, but the logistic one gave you 69% correct predictions. So it's much better as we have seen based on these results. Simply because this one is the logistic is parametric classifiers, and then the KN is non-parametric one. With some previous assumed distribution, it can give better results. Okay. So next one is we just introduced today, which is the linear discriminant analysis. So this one is an interesting classifier here. So in general, the logistic regression involves directly modeling the probability of y equals to k given x. So this is in general, this will be the normal process we will use in OS or logistic regressions. So like so for example, we want to produce if the family will buy eco-labeled apples, and then we give all the features like the age, race, family income. So we give all these observations, educations, and then we predict the results, predict this column based on these features. But for the linear discriminant analysis, this one actually predict in the other way around. In the linear discriminant analysis, we model the distribution of predictor x separately in each of the response classes. So in other words, it first predict the probability of x equals to small x given y equals to k. So it reversed the prediction. Like this one is the conditional probability of y given x. This one, so in the LDA, we first calculate the conditional probability of x given y. Okay, and then we follow the Bayes theorem or the Bayes rule. As we have probability of y given x, this one equals to probability of y equals to k times the probability of x given y equals to k. This one is just the Bayes rule. So you do need to be familiar with this one when we introduce the regression, introduce the classifier. Okay, so this is the Bayes rule here. Make sure you do familiar with this one. And one thing interesting is, so probability of x, this one is actually equal to summation of probability of x given y times the probability of y. This is also part of the Bayes rule. And then after you do some derivations, you will get these results. Okay. And so this model actually, the LDA classifier introduced in the other way around. So it actually learns the difference between, you can think something like this one. So suppose you're in, suppose you have two children, and then you let them to go to the zoo. So in general case, we want, one of the cases actually learning that, like there's a long nose for the elephant, and then one is tiger, one is elephant. So actually learn every features of the two animals, and then after outside of the zoo, if you can see a picture like a pink animal with long nose, then these children know like it's an elephant based on all the features he had already observed. And the other case only check the difference between these two kinds of animals. So one is elephant, one is tiger, and then he only check difference. So one is larger than the other one, like elephant is larger than tiger. And then also the color is different. So once he saw an animal, he will see like check the color and then use difference to learn to classify which kind of animal this is. So he will classify when he saw like a picture of tiger, he will just notice like the color is not the same as elephant. So he will classify this one as a tiger. So this is just the reverse way of, it's not reverse way, it's just different way of predict the independent variable based on the observations. And then this one, the LDA one is in general, it's based on the Bayes rule here. And then so the professor has introduced this classifier in class, and then I will not be specify about like how we derive this one. Just this part is on chapter 4 on the textbook. So chapter 4 here. So you can see. Here. So this one is a Bayes rule, and then so the pi here will introduce a prior probability. This one is the probability of y equals to k. Probability of x given y equals to k. Sorry. And then so with all these, this is the distribution of normal distribution. And then you do some derivations, you will get this classifier. So the professor has introduced this form in class. And then you can go, if you're interested, you can do this derivation by yourself. See if you can get exactly the same results as the test. Okay, so the next step, so any questions so far about how we derive the classifier for the LDA? Any question? Okay, so so next step we are going to use is how we train the LDA in R. So similar as before, we choose the same features: education, age, family income, household size, regular price of regular apples, price of eco-labeled apples, and then we do the training here. Just use these two lines. So for all these functions, you will need to check which kind of arguments they are taking. Like it takes X, which represents for the matrix or data frame or matrix containing the explanatory variables. But first of all, so this one, all this part here is in the formula part. So we want to regress this and then we'll buy eco-label apples on education, age, all these features. And then you will get these results. So this what LD1 represents for linear discriminant 1. And then in several cases, there may be, there are like two dimensions in some cases. Here. So you can see it has 2 dimensions with the plots here. But for this one, we only have 1 dimension. So we will only draw, when we draw the graph, it will be a straight line. And then with the histogram, I will introduce this one later. And then so in this LDA variable, you can see, you can check their priori district probabilities. This one is calculated based on the observed, based on the observations. Like how many of the observations in the training size they are classified as group 0, and how many of those are classified as group 1. So you can see like 37% of the group of the observation data are classified in group 0. And then the scaling one, this one is the coefficients. So once you check, so let's check. Scaling. So this number, you can see this one are just exactly the same as the coefficient here. So scaling, the scaling value provide a matrix which transform observation to discriminant functions, normalized so that within groups covariance matrix is spherical. So this one, once you use this matrix times the training data, you will get the score for each of the linear discriminant. And then so this plot function produce plots of the linear discriminant obtained by computing. So here, so you use all the results. So like we use 0.15 times the education in the training data set, and then minus 0.0029 times the age, and then plus all these. So this number times family income, this one times the household size, all these things until the end of those things. And then this one is introduced as linear discriminant for each training observations. So in this example, we have 524 observations. So after we do the LDA cut, we do the LDA regression, we will have 524 training linear discriminants based on each of the training observations. And then this one, this graph. So LDA in this package, the LDA contains a plot function which you can let's So this is the plot method for class LDA. And then it will directly plot. So here's the description. So for dimension is bigger than 2, a pairs plot is used. Dimension equals to, they will draw a two-dimensional graph. For dimension equals 1, this one will draw a histogram or like density or both. So you can choose. And then this one just show you like based on the linear discriminants which we introduced before, like use this coefficient times the observed data sets. You will get the results, and then the horizontal axis is the linear discriminant, and then the vertical axis is the probability. And then you can see, so we have two groups, and then you can see there's like if they are overlapping or like how they classify the how the LDA classifier train the data sets and then separate two groups. And then we will use the predict function to predict the list of to predict the out of sample. So given the test data sets, which contains 136 observations, so we use the features inside this test sets, and then this predict function returns a list of 3 elements. So this one is also checked.
Yeah, you do. You got some pretty good resistance around here.
Sorry? Any question?
If you can.
Sorry, I cannot hear.
If you can start on a river on the.
Sorry, I cannot hear you. Hello?
Sorry, I think my microphone was on by accident. I don't have a question.
Okay. So this is how we check the prediction function for LDA, and then so I will take the arguments like the objects data, and then if you want to specify the prior probability for the product for the objects, and then so it will return 3 values: class, posterior, and then the x. The class represents for the MAP classification. This one represents for maximum A posterior classification. So I'm not going to introduce this one in the class, but if you're interested in this one, MAP represents maximum A posterior probability estimates. Okay? So in general, after we run this regression, we run this, this predict function, you will get 3 values: class, posterior, and x. So here, these 3 things. So this factor, the first elements in this, the first value here is just it's a bunch of 0 and 1s. So it's based on the posterior here. So so you can see here for the first one, because the posterior probability gave you like for 1 is bigger than 0.54, then it will be classified as 1. So all the things you can see all the same until this one. So this one is just for this one, the posterior probability is for 0 is larger than the posterior probability for 1. So it will classify as 0. And then this x is just linear discriminant, which we have introduced before. And then I put some details in the PDF file so you can read later. The x contains the linear discriminant, which is introduced here, this part. Use each kind of the coefficients times the observed features. Okay? And so our predictions is based on the class value inside the prediction function. And then we use same methods, which we test the mean and the table. So here we see we got 21 correct predictions when the true value is 0, and then we got the prediction of 0. And then we got 75 correct predictions for the true value equals to 1, and then prediction equals to 1. And then in general, we got 70% correct predictions based on test data sets. Okay. So every time when we do the regression, use different kind of classifier, we will use same methods. So in the binary case, we will test how many correct predictions based on the mean here. And if it's not binary case, first of all, you may not use logistic or this analysis for non-binary case, but you can still use something like maximum mean square error or like absolute error to get how you test the accuracy of the regressions. So you should be familiar with this one. So this one is just in general how we test the accuracy of the regressions, the mean square error or like the absolute error. And then that one gives you the accuracy for this regression. Okay. And then the last one is introduced is the QDA classifier, the quadratic discriminant analysis. So similar to LDA, the QDA classifier results from assuming the observation from each class are drawn from a Gaussian distribution. So all of these, both LDA and QDA, they assume that the prior density function is normal density function. And then you plug in all the estimates for the parameter into the Bayes theorem in order to perform predictions. But the difference between QDA and LDA just assume that an observation from the case class is with normal distribution with mu k and sigma k. So for the LDA, we assume this one is the same for all the classes, like for k equals to 1 to k. For all the classes, they will share the same covariance matrix. But for the QDA, we assume different kind of covariance matrix for the k class. And then the classifier is defined as this one. It's similar as before, but just with different kind of with different covariance matrices, you will get a quadratic form at the end. So as you can see, when we introduce the LDA classifier, there's only one x here. And then when we introduce the QDA here, the classifier is quadratic form in x. So that's why it's called QDA. And in general, LDA and QDA may perform similar if we have if the LDA assume like the same covariance matrix for all the data sets. But in other words, if there's if the covariance matrix are actually large different, so say 1 is -5, 1. So 1 is -0.5, 1 is 0.5. Then the QDA will give you better prediction based on different covariance matrices. Okay. And this one is in general, this one is similar to the LDA regression. So this one, we introduced the QDA function here. So all these things are all of these functions are in the mass package. So make sure you do install the package before do the regression. And then similar as before, we use same features. We use these 6 features, and then I will show you the results for the QDA regression. And then similar as before, you can check the predict QDA. So this is the prediction function for the quadratic discriminant analysis. And then we predict the QDA predict the testing sets based on the training. Sorry. So we predict the data sets based on the training coefficients. So once we do the prediction, difference between QDA predict this one, so difference is just LDA contains one more values in the function, but it's still the same. It's still similar. And then we also want to pull out the class value out of the QDA. So we pull out the class value, which one is introduced as the MPA classification here. And then we use the mean function and use the table similar as before to test the accuracy. So here's the case. The QDA predict got, like, in general 96 correct predictions, which is 70.5% out of the testing data sets. So this number is the same as the LDA. So these numbers are the same. This is just because when we, like for the LDA, it's assumed they have the same covariance matrix, and the QDA, even though it assumed like different kind of covariance matrices, it still gave you similar results. And the reason for people in general they will use LDA is just because LDA is much easier. It takes less computation tasks, and the other way is just use LDA will reduce the variance for the results. And if I have time, I can show you like the example in textbook. Okay. So let's do the comparison between these four kind of different classifiers. So make sure you recognize this one is non-parametric. Then all these three belongs to the parametric classifiers. Okay. Let's run this comparisons. Okay. So we check the first 20 predictions for each kind of method. And you can compare, let's just take first 5. So this one belongs to the KNN method. This one is the LDA. This one is logistic regression. This one is the QDA. So you can see there do have slightly difference between QDA and LDA. I gave you different results because they are using different methods. And then this is tables compare the true value with each kind of predictions. So all this column represents for the predictions. And then this horizontal value represents for the true value. So the interesting here is the LDA one and the QDA. So you can see most of the case, even though they get the same accuracy based on the testing sets, but it gives you like 22 correct predictions for the true value when the true value equal to 0. This one gives you only 21. And then wrong predictions are also different. So even though they give the same results, they are still using different classifier methods. So it still depends. Every time when you try to face different kind of scenario based on different data sets, you still need to figure out which classifier you want to use. Is it in general, is it OLS? Is OLS better than logistic one, or logistics better than OLS? Or you want to use some parametric and non-parametric classifier? And then if you want to choose LD. So these are the like the R coding I'm going to introduce this week. And then so after you have all this data, so for each week the homework is determined by the professor, and then it may cover something like you may need to do some problems that we haven't introduced. So in this R markdown file, you should get all the things you want to do for this week homework. And for the homework, in general, we roughly check if you complete the homework. So make sure we just want to make sure you do some practice and then you do the problems. And then, so here's the graph here. So make sure you do go over these graphs in details after class. This one is the page 152 in chapter 4. So this one gives you like the comparison between each kind of method. So this one, the KNCV represents for the cross-validation. And then you can see the QDA performs better than, the QDA can perform better than other cases in some scenario. It can also give you like a results with high variance in some case, because QDA is more sensitive to the classifiers. I'm sorry, more sensitive to the outliers. And then using different covariance matrix, it can give you like a bunch of noise results compared to the LDA. So you can see there's still some outliers here, but it will not like conflict with the correct predictions here. And so these graphs are along with these scenarios. So you will need to check for each of the scenario which one give you better results. So when they have correlation of -5, you can see we have the LDA or the logistic give you better results than the other three. Let's see what the counts is going to say. Okay, yeah. So I will hold office hour on Monday starting next week, and the professor will start to hold office hour, I think, the week after next week. I'm not sure. I will hold office hour weekly on Monday from 4 to 5 p.m. And then the invitation link is on Canvas. So you can just click this link to get into the office hour room in the Zoom. Okay. And you have one homework due tonight. Okay. Any question? Yeah. Sorry? You mean current? So why this one has this? Okay, that's a good question, but let's see if I have time to do this. So in general, the two classifier in LDA and QDA, they just in general they will use the same way to do the classification, but so you can see this this classifier. It takes the log form of this one. So this one is just simply when we plug in all the normal distribution, you do the let me use another way to illustrate this one. Okay. So once you take the log transform of this function, you will get a results. I'm not sure if my tablets work here. Let me check. So this one, sorry, it seems better. Oh, okay. Once you take the log transformation of the pkx here. Can you see my handwriting? once you take the log transform, this one will be proportional to log pi x pi k plus so in general, it will be proportional to this part. This is the numerator in the probability I just showed. And then all the other things, because they are not, the reason I only introduced the numerical part is just this one, the denominator does not, this one is not related to k. So only the part introduced with related to k will be here. And then once you once you do the formal transformation, this one will give you something like log pi k. And then because this part has nothing related with k, so we can ignore this part. And then minus 2 pi square, 2 sigma square, x minus mu k. And then once you do this part, you can further do the derivations. This one will be 2 sigma square x square minus 2x mu k plus mu k square. So you can see here, this term has nothing related with k. So there's nothing related with k. You can also ignore this part. And then at the end, the classifier will be x, because these two cancel each other. You will have x times mu k divided by sigma square minus mu k square plus log k. So this one will be the results for the classifier for the LDA. And then when you do the QDA, it follows the same way, follow the same derivations, but based on different kind of the covariance matrix. You cannot just simply, you can think about like in the QDA part, this sigma is no longer a constant. So this one may become like something like sigma k squared. So this one is no longer, so this one is actually related to the k class. So it's no longer, you can no longer ignore this term. And then you will get this x term here in the QDA classifier. Is it clear? It's just like, it's kind of the derivations, but it's sometimes you want to do that, but we won't. I don't think the professor asked you guys to know how to do the derivations. Okay. Another question? Okay, so if we don't have question, we will end up here today. Okay. Good night.